So let's validate and first understand the sample problem from the book. So here, as you can observe, that this particular problem involves calculating the stresses in the copper and steel wires due to the temperature rise. So here two things are involved. One is regarding the load and another is related to the temperature. So we'll walk you through how this problem is set up in Staad, and then we will verify this particular results which the book has given. Although this particular segment is not specified manually in the book, but we will try to replicate the same sample problem in the Staad. So you will be able to understand what points you need to take care while implementing such calculation, and to resemble the similarity between the sample problem versus its actual behavior in the Staad modeling. Alright, so they have specified the answer as well over here for the stress in copper and this particular segment. So in this problem we have this rigid horizontal member suspended by these wires in this particular two made out of which two made of copper and one is made of steel. Now due to the temperature rise of 10 degree, the wires will expand and we need to calculate the resulting stresses. So ultimately we will try to work out this particular answer, whether we are getting the actual answer in the Staad or not, right? And based on the data provided by the sample problem from the book, here are the segment for the copper wire and steel wire. You can check out these values of E and Poisson's ratio, then the coefficients of thermal expansion that is already provided in the sample problem over here. Now as E and the alpha value are already specified over here, so instead we need to replicate these values in the form of the material. So in Staad model we will model this particular material category and create that particular material, and then we will implement that in the property part, right? For the property part it is also specified here the E value and the length value. Okay, so we will replicate this and try to work out whether we can able to get the validation or not. Now for your understanding, as you can see over here, the similar segment over here which is available, right? We have model this particular segment 1, 2, 3, right? Here the cross-sectional area is 0.1 inch square, length is 20 inch, and the load is 400 pounds per inch, right? And this particular load we have implemented over here. Now another important thing I want to highlight over here is that let me just take you through the problem. Okay, here the load is provided in the concentrated form as a point load, okay, which is specified as in 4000 pound, right? Now while modeling this particular segment, see here this segment has very large moment of inertia, right? So when modeling we assume that a large moment of inertia for this particular horizontal rigid member, and we will distribute that particular concentrated load as in uniform load. Alright, as is the rigid segment. So basically the horizontal member is assumed to be very rigid, so it will not deform, right? And the load is uniformly distributed due to the large moment of inertia of the horizontal segment, right? Then see, as you can observe over here, I have provided two segments of the relays. So let's understand this segment in the Staad model. Okay, so basically this one is copper 1 and 3, and member 2 is steel. So let's check out the Staad model over here. Now firstly I'll brief you about the material part that I have implemented over here based on the property that they have provided, right? So similarly you can develop a new material with the same values that is already given and I have discussed with you. You can check out this with the thermal coefficient, and this is another value, right? These are the values from the data itself. So I have created this two material 1 for this 2 and material 2 is for this segment. Once you create, you can create it from here. Okay, so you can enter the values and create the materials. Now the same segment, as these are the wire forms and the area given is 0.1, right? It is already specified over here. Let's check out, right? Area is already given 0.1 inch square, 0.1 inch square, right? So same I have replicated over here, right? Now as it's a wire form, I have kept it 0.1 inch square for that wire segment, right? Now the bottom segment we are assuming is very rigid, so in that particular case the area is 1 inch square, but the section modulus is comparatively very higher, right? So that's how these two prismatic segments are replicated over here, right? Then to replicate the behavior of the wire, right, we have specified the release segment. Now this is very important portion. At the top segment I have released MPZ as the 0.99, and at the end the MZ segment is released. So the next important question that comes in your mind is that, sir, why we are providing the release, right? And see, as you can see over here, this segment is in the form of wire which is suspended with the rigid body. Alright, so instead basically releasing moments at the ends of the members allow for the simulation of this specific structural behavior, and the commands that you have seen, that is MPZ as 0.99 at one end and MZ at the other end, are related to the how this particular moments, particularly in these Z directions, are handled at the member ends, right? So ultimately if I switch to the Staad segment, see, releasing moments, the MZ, this command fully release. If I talk about the MZ part, this command fully releases the moment in the Z direction at the specified end of the member, making that end behave like a hinge. And in this case the member cannot resist any moment about the Z axis at this particular end, alright, allowing it for the free rotation around this axis. Next was the MPZ segment, right? See, it is released 0.99. See, this partial release indicates that 99% of the moment in the Z direction is released, but 1% of the moment remains the restraint. So this partial release is also used to replicate the near hinge condition, where the member end has very little resistance to rotation but not entirely zero. Okay, so we have this combination of moment MPZ, that is the partial moment release 0.99, and MZ. So basically why this combination? So by releasing 99% of the moment at one end and fully releasing moment to the other end, the model can simulate this particular structural response where the connection at one end is almost a hinge but still retains the minimal moment resistance. So this small restraint, 1% of the moment, can represent a connection that isn't fully pinned but still allowed for the slight resistance to the rotation. So in contrast, the other end with a full MZ release allows for the complete rotation, simulating a simple hinge. Another important point is you can prevent another important point I can say is to preventing the numerical instability, right? You can observe we have this wired stick over here which is fixed, but in the other case if you thought in the form of instability, sometimes a full moment release at the both ends of the member might lead to the numerical instability, correct? You get the instability errors, right? So by retaining a small fraction of that moment resistance is like 1%. Another point you can think is about the preventing the numerical instability. You can observe we have both the end hinge, right? So sometimes the full moment release at both ends of the member might lead to the numerical instability, or we got difficulties in converging to a solution, right, in the form of error in Staad. So by retaining a small fraction of the moment resistance, like the 1% as I have specified, it can help in stabilizing the analysis. So in our specific problem, where a rigid bar is suspended by the two copper wires and a steel wire, the moment releases are likely to being used to model the connection between the rigid bar and the wires more accurately, right? So the bar is considered rigid so that the moment release on the wires help to ensure that the connection can accommodate the behavior expected from the rigid body while still providing some level of rotational restraint. So this setup allows Staad to model the behavior of the rigid bar and the attached wires more realistically, ensuring that the structural response closely matches the physical expectation. So that is what the important point I want to highlight over here, that how you are understanding the structural behavior. Based on that behavior, you can replicate those behaviors in Staad as well, but you should have clear understanding of the structural's actual behavior, and that also helps software to get the accurate results. So that's what the release portion, see, based on once you specify the release portion, let me just show you again. See, at the end, as it's the rigid function, mz is fully rigid, and here we have released 0.99, right? Now once you finish this setup, we will switch to the loading part. Now as you can observe over here, let me just scale this. You can scale this from here. Let me just go to the structural diagram, scale. The scale is bit higher for the distribution force. Right, now it's proper. So I have implemented that point load in terms of the distribution force, 400 pounds per inch. So ultimately that point load is converted into the UTL, that's it, right? And we have the temperature variation. So temperature load is implemented on the members. Temperature change for the axial elongation 10 degree, right? So these are the two loads that we have implemented. Now to check, to get the results of the stresses, we need to incorporate the command manually, that you already know, right? So we have discussed this in previous problem, right? So I'll enter the command as perform analysis, and what we need to enter, we want to get the stresses, right, for a particular segment. So I'll enter the command as print member stresses, and we will list out the members, list 1 2 3, right? Now see, one important tip I want to highlight over here is, once you finished your syntax portion, or let's say you are editing your editor manually, what you can do is you can click here for checking the syntax whether it is correct or not. So I'm getting some warning. Warning, member 2 has already had a material assigned, the last assigned material will be used. Okay, so it is a warning, right? But let's say if you made any mistake while listing something, or let me just show you. Okay, so let's say I'll make an error and check syntax. So see, it is showing me error that we have not entered the command properly, right? So check syntax is another useful tool so that you can avoid running the analysis simultaneously. So you can use this segment. Let me just check it again. Okay, so this is the warning only, so we can ignore this. Now I'll run the analysis, and let's first check what are the answers. So I'm getting stress value over here for the steel as 19,700 pound, and another one is 10,200. So let's hope that we get a similar results. So we'll run the analysis. So here I just want to highlight the importance of the structural behavior and their replication in the Staad. That's what I want to convey over here. Though it's not a manual validation, we are validating those values whether we are actually getting or not, based on what? Based on our understanding of the structural behavior. Alright, see, so we have the member stresses printed over here, and you can check that we are getting the accurate near about values or results. Okay, so here what was the value for steel? We have 19,700, and here I'm getting 19,698. So it's a negligible value, right? Similarly, for the copper segment we have 10,200, and here I'm getting as 10,150. So the results are almost negligible. You can say that we have a slight difference in the answer, but the main important part over here is replication of the structural behavior in Staad. So these are the small understanding that you need to take care while designing these structures, whether it's an RCC or steel, or you can say if you are designing any particular segment in the let's say in the framing plant. So how you are replicating those connections, let's say if you are planning connections, whether it's a slotted connection or let's say shear connection, moment connection. I'm just giving you an example. So all these behaviors are very much necessary in order to replicate this in software, and that's where we usually always encourage students to understand the concepts and the structural behavior so that it will help them through the software. Okay, I hope this particular video gives you more understanding about the structural behavior. Share and like this video if you found that we are bringing value to your structural engineering concepts. And always remember, don't just learn software, learn concepts. Thank you so much.